Hi, my name is Emma Heslop, here at IOC UNESCO, and this is the next in the series of the GOOS webinars. Thank you very much for joining, and I hope you're going to enjoy this really excellent presentation and hopefully have a good discussion afterwards. We have to present here Dr. Magdalena Balmaceda of the European Centre for Medium Range Weather Forecasts, or otherwise known as ECMWF, based in around near Reading in the UK. And Magdalena is going to talk to us today about the increasing role of ocean observations in weather and climate predictions at a very exciting time, apparently, so I understand, for ECMWF, as they've just added climate and an ice model into the daily predictions. But Magdalena can correct me if I've got that wrong and give you some more news. First of all, I just want to give a couple of pointers for the webinar this afternoon. We probably will have a presentation of around about 30 minutes. In the toolbar on your left-hand side of your screen for the attendees, you should be able to locate something that says something like questions, and into this questions box you can type your questions, and then I will help moderate that at the end of the session, and you know, read out some of the questions to Magdalena. So you can type them in at any point at the end or as we're going through the presentation. And this will also be recorded, and if you want to make the presentation, the PowerPoint, larger, then you should be able to move a kind of a grey bar near the top of the screen up and down to minimize or maximize the video and the presentation. So that's up to you. I think that's it. So I'm going to hand over now to Magdalena for the presentation, and I'm going to disappear off so that she can get on with the big job. Okay, so thank you very much, and a big welcome to Magdalena. Okay.
Okay, thank you, Emma. Hello to everybody. It's the first time that I give a webinar, so I'm not accustomed to talk on my own without looking at the audience. And I'm feeling a little bit self-conscious because I see myself on the screen. So I'm going to try to switch myself off, if it's okay for you, and proceed with the presentation. Yeah, okay. I think this is fine. So I want to talk to you about the increasing role of the ocean observations in weather and climate predictions. And when I say predictions, it means initialize predictions. So we need to know the state of the real system of nature now. This is going to be very much a perspective from ECMWF, which doesn't reflect what is happening everywhere else, but well, it does reflect what is happening everywhere else. And I want to thank all the colleagues of ECMWF that have helped me to prepare this presentation. Yeah, so one of the important things that I want to say, first of all, is that the fact that the ocean is part of the weather and climate predictions, it adds another dimension to the relevance of the ocean observations for society, as you can see from some of the slides, that are photographs that I put here on the right-hand side. So let me see if I can. This seems to be a little bit slow. Let me see if I can proceed. The outline of my talk is to talk a bit about what we say seamless forecasting systems. That is the same sort of system from days to years for weather prediction and weather prediction of weather statistics. And I also want to talk to you about the importance of reanalysis activities. The reanalysis are really an integral part of any forecasting system, and I hope I can convey that information to you during this presentation. I also want to talk about recent perspectives. I mean, there is a lot of activity going on that I will try to highlight, and that's regarding with the related to the new program on subseasonal to seasonal predictions, where observations, ocean observations, are going to play quite a role. Couple data simulation activities and couple reanalysis. And finally, I will try to summarize all of this. So, what is ECMWF? I mean, ECMWF is the European Center for Medium Range Weather Forecast. And ever since it started, this mission of a medium range, or the meaning of medium, has been expanding. So we started with a forecast medium range was 10 days. Now it's probably 15 days. But we also do monthly forecasts called extended range predictions. And there we care more about weekly anomalies rather than just individual events. Is what is going to happen during 1 week, weather regimes. And of course, we have the seasonal predictions, also called long-range predictions, up to 6 months, sometimes up to 1 year. And those are based on El Nino predictions, among other things, but El Nino is the main important component. Because of this expanding in the time range of the predictions, we cannot ignore other components of the Earth system that are not the atmosphere. So ECMWF has embraced what is called the Earth system approach to be able to predict up to 1 year ahead. We really need the ocean. We knew that. Seasonal forecasting needs the ocean, and in fact that was the vehicle or the way in which the ocean activities started at ECMWF. Little by little, that ocean has been kicking up or down to the medium range, as I will explain. So we have ocean, sea ice, waves. We have also atmospheric composition, and of course, the traditional land and atmosphere processes. This is a bit busy slide, but let me explain it. This box here, that is very simple, is our Earth system in a nutshell. When we launch a prediction, we will need an atmosphere, land, waves, ocean, and sea ice, and all these components are coupled. But these components need to be initialized. That means we need observations to blend the state of the model with the state of nature. So we need a real-time analysis or reanalysis of all these components: ocean, sea ice, waves, land, and atmosphere. So what do we do with this model and these initial conditions? Every day, twice daily, we launch an ensemble of 50 members, a forecast for weather. It's coupled to the ocean, so we have 50 realization of the ocean twice daily, every day, twice daily, up to 15 days. Twice weekly, on Thursdays and Mondays, there is an extension of this forecast up to 46 days, also 51 ensemble members. And there are 51 realizations of the future ocean. Monthly, we have an extension up to 7 months. That's the seasonal forecast. Again, 50 members or 51 ensemble members, 51 realizations of the future of the ocean and the atmosphere as well, obviously. But I say ocean because we are not so familiar in oceanography. We are not so familiar with this sort of predictions. And once and quarterly, we extend this prediction up to 12 months. Something interesting as well is that all these predictions, they are going to public databases. The most interesting database, probably the most recent database for the public, is this Copernicus Climate Change Service, C3S, that will provide ocean variables. There is also the so-called S2S, subseasonal to seasonal database, that will provide ocean variables. At the moment, there are not ocean variables there. And there is this other TIGI database for the medium range that doesn't have ocean variables, but it will in the future, I think. So the most important thing is that this data will be available, that the ocean is an integral part of the forecasting system, and we need ocean observations in real time, every day. And in fact, we monitor these ocean observations. They come via the GPS, and we have this capability for observation monitoring and tell us how the model fits the data and flag observations. And it also points what is the coverage of observations. This is just one snapshot of in a 5-day window, recent 5-day windows, what is the coverage. These observations are going into the forecast during that period of time. I mentioned before reanalysis, and so far I mentioned the real time, but why reanalysis? So when we launch a weather prediction, consists on a realization of the possible outcomes of the weather that we sample, launching some ensembles, some say 50 different realizations, so we can sample the probability of what the atmosphere may do. But the model is not perfect. It's also that if we want to talk about extreme events, we want to refer it to the past. So what we do for that, for this PDF to have a value for users, is we launch, we calibrate it. And this is done by launching many of these, we say reforecast. Instead of real time, we do it for the historical period. So we can estimate what is the climatological probability of the model. And with that, we calibrate or forecast, and by comparing what happens today, what would have happened in the past, in the climate. So these reforecasts are essential for to give value to the couple forecasts, and they have to be initialized from reanalysis. If the forecast model is a couple, that means that we will need to have an ocean, atmosphere, sea ice, and land reanalysis. Otherwise, we cannot initialize these reforecasts. So what are the reforecasts are needed first for calibration, as I mentioned, detection of extreme events, is a growing activity, and also for a skill estimation. It's not enough to launch a forecast, to give a forecast. We need to have an idea of how good that forecast is. Otherwise, everybody could produce a forecast. So at ECMWF, we take skill estimation very seriously. At least we know the deficiencies. And for that, we have an ocean reanalysis that is brought continuously up to real time. It's called ORAS-5, and it goes back to 79. And here you can see some statistics for temperature and salinity fit to the observations. For reference, this is ORAS-5, the RMS error. These are the evolution in the number of observations that we obtain. The reference, this we call it the control, is one ocean simulation without data simulation. So the data simulation using these observations really helps to constrain the state of the ocean. But data simulation is not the whole thing for the ocean observations. So the observations, they have many different purposes, many different lives. So if you think on one observation today that is being measured today, so probably it's going to go, if we receive it on time, for the initialization of today's forecast. NWP, monthly, and seasonal. But if it doesn't arrive on time, maybe we use it for verification of yesterday's forecast, or last month, or last season. So this verification process is really important for forecasting because it tells us about the weakness and strengths. If it arrives, a little bit later, maybe a few days behind real time, it still can go to the monitoring of climate conditions for the reanalysis. And if it goes into reanalysis, imagine it doesn't go to the monitoring because it has to be quality controlled. It may go to the reanalysis that is going to the next generation, so ERA 6, for instance. So that will mean that it's going to influence the forecast calibration and extreme event detections in 5 years' time or beyond. And finally, the observations are always used for improving the forecasting systems, the model development, the data simulation. That's slower, but the observation today will contribute to improve the forecasting systems used in the next decade. So the impact of all the observations on all these different aspects is not easy to quantify objectively, but it's there, so we shouldn't forget it. So I'm going to start now on revising a little bit how we use the observations, or some issues that we have, some highlights. So as I said before, we started using the ocean and the ocean observations about 20 years ago when we started the seasonal forecast activities at ECMWF. So our first system was a pilot. It was implemented in around 1997, and it was called System 1. Since then, we have had changing the systems every 5 years, more or less. And last year, in November 2017, we implemented the new system SYS5. And we monitor progress. Progress is very slow, but exists. It's not easy to get this improvement in a skill. It takes 20 years. So patience is needed. But you can see here what I try to illustrate is the forecast lead month in a forecast that it goes up to 6 months. When the correlation is 0.9, is pretty good forecast. And this is a measure, an index for ENSO, Nino 3.4 SST anomalies. Is the very standard index that we use. And you can see how we have gained about almost 2 months of skill in ENSO predictions in the last 20 years. That's pretty good, I would say. Gaining 2 months on forecast range is, I mean, we are very proud. You could ask the question, what would happen if we didn't have ocean observations to initialize the ocean? Because these predictions are based on this ocean reanalysis that combine observation, all the observations. So if we only had ocean models and SST and the winds from the atmospheric reanalysis, what would happen? So the forecast, this is an equivalent experiment, will drop, the forecast lead time will drop substantially. So we probably, all the observations that we assimilate is equivalent of 15 years of progress in modeling or ENSO prediction. So that puts things into perspective. Even if it looks very little, when you look at curves, it's 15 years. So something to bear in mind. So that figure before showed the impact of the ocean observations on the initialization, but there has also been progress on understanding and model improvement. You know? As an example, I can show here the forecast, the reforecast in 1997 for the 1997 El Nino for the different systems. I don't know whether you can see it, but at the beginning, the orange and the green, the forecast, they were not able to capture the amplitude of ENSO because they didn't have the MGO on the Magdal oscillation, that is called the intraseasonal variability, that is responsible for the westerly wind burst. It was not only until System 4 that we gained, we could able to reproduce, but mind you, we overestimated the amplitude a little bit. With the new system, this prediction seems to be quite good, at least for this event. And this is the result of using observations for model improvement. Now I'm going to change, I'm going down time scales, and I'm going to talk about the sub-seasonal forecast or extended range forecast at ECMWF, which at ECMWF are up to 45 days. This is an example. This also uses ocean observations, but this is an example of a prediction of the cold wave that we experienced last winter. In terms, I don't know whether you remember, over Europe, and I think it was also over the US. This is the very fine analysis, and those are predictions at different lead times, week 1, week 2, well, five days, every 5 days. You can see here in the bottom panel that this event was well predicted 20 or almost 30 days in advance. So 30 days in advance, the system was giving us a warning that we could have cold anomalies over Europe. And where the skill comes from? The skill of this subseasonal forecast also comes from the tropics, among other things, but the backbone of the prediction is what is called the Magdal oscillation, which is a convective anomaly, and you can see it in terms of outgoing long wave radiation. It's like a moist Kelvin wave that propagates around the globe with, and it's relatively periodic. Well, it has from 30 to 60 days time scale. And when it involves deep tropical convection, and depending on the position of this tropical convection, it can influence mid-latitudes via Rossby waves. So we know that there is more skill in mid-latitudes when we have when the MDO is strong, and it influences the occurrence of North Atlantic weather regimes. The impact of ocean observations at this time scale has been very little explored, or not at all, but we are starting now, and I think this is quite an exciting development. It's going to be a strong focus for the S2, SW, WMO, WCRP second phase. I mean, this is just an evidence. It's very little, but that's where what we based on decisions on implementing forecasting systems. This graphic shows the predictions of this Magdal oscillation with a couple model, and this is if they are not, if we had observed SSTs. So this is something that we will never have in a forecast because we don't have the observed SSTs, they are reforecast. But this graphic shows that the skill is better when we couple the model, just because to represent we need to represent well the Earth interaction, which is essential for the propagation of this Magdal oscillation. This was this sort of examples of experiments are the ones that guide our developments of forecasting systems. The MGO, or the Magdal oscillation, depending on where it is, it modulates the impact and the tropical cyclone density. So if it's over the Atlantic, it's going to have, you are going to have more tropical cyclones on this area. If it's on the maritime continent, you are going to have more typhoons. And if it's more on the eastern Pacific, one is going to have more tropical cyclones in this area. On the right panel, you can see how the model is able to generate that. We have conducted some observing system experiments. This one is with altimeter, not in situ observations. But it shows that if we didn't assimilate sea level from altimeter, the skill in predicting tropical cyclone at the monthly time scales, day 16 to 45, it will drop. So this monthly forecasting system is good to give some alerts on the probability of tropical cyclones, and yeah, ocean observations contribute to that. For the medium range, ocean observations have always been used in terms of wind, waves, and mean sea level pressure. And here is we use them for monitoring and also for assimilation. And I had a request from one colleague saying that the mean sea level pressure from the buoys is significantly better than from ship, and the improved NWP. So his question was whether there are not enough mean sea level pressure sensors on the drifting buoys. So if they could be equipped, it could be beneficial. As I mentioned before, the highlight is this from the 6th of June 2018, all ECMWF forecasting system, including what we call the deterministic or the high resolution. They all include the dynamical ocean and sea ice components. And these are graphics showing, and blue means good. Is the coupling improves the errors. I mean, reduces the errors of the weather forecasts, especially in the tropics, as you can see. So we have adopted, we have decided to couple the ocean and the sea ice. Let me see if I can play this movie, because the ocean, this is a movie for the hurricane Irma, and later on you will see Jose. The coupling is supposed to be also very important for the predicting the correct intensity of tropical cyclones. And it's because of the interactions with the ocean. You can see the cold wake of the hurricane. And if you didn't have an ocean, you wouldn't get this, and the intensity will be overestimated. You can also see how on the pulsating SST, the diurnal cycle, no? So that's quite interesting. And Christian used these 3 buoys here, where the cold wave goes, to see how the model and the forecast behaved. So those are these moorings. No, they are moorings, they are buoys, sorry. And this is how the model predicts it. And you can see that it gets the cold wave, not with the full intensity, but it's relatively good predictions. And it also is able to predict the fluctuations of the diurnal cycle. In some cases, it's better than in others. Here, the model has a cold bias, but it predicts the variability. So the diurnal cycle is really important, and there are efforts trying to see how the diurnal cycle, both not only of sea surface temperature, but on the ocean and on the atmospheric boundary layer, rectifies and impacts the forecast. This is the number of observations that where they are sufficient enough to sample the diurnal cycles. And here you see the tau moorings, and that they have enough observations of the diurnal cycles. Now I'm going to change to coupled data simulation and coupled reanalysis. So it's a bit of a different subject, but it's also quite exciting. So recently, there were a couple data simulation activities out of some research projects, and in particularly this Iraclim 2 project funded by the EU allowed us to conduct 2 reanalyses, one couple reanalysis for the 20th century, based on conventional surface and subsurface observations, and CIRA-SAT, a couple reanalysis at high resolution during the satellite era. This one is being analyzed now, and it continues in quasi-real time. So we are quite, we are looking forward to have the time to analyze this data. One of the first things that arose from these experiments is that the importance of the coupling for the simulating the energy balance, if you want, to the energy cycle in the analysis. And uncoupled data simulation, you will see it in red. The simulation increments at the what the ocean observations are doing at the bottom is opposite from the surface fluxes is doing. So they are correcting each other and they are incompatible. And you see that trend going increasing. However, in coupled data simulation, there is much more consistency in the surface fluxes and the ocean observations, the fluxes from ocean observations. So we think this is this approach could bring quite a lot of benefit for the reanalysis for climate. But of course, it's a long way to go. The problem is not easy. We also are quite excited with the idea of measuring the impact, for instance, of scatterometer winds on ocean salinity. So how one observation from one media can influence the other media. So these are some experiments with drawing the scatterometer winds. Can we see anything in the ocean? You can see here, yeah, it influences temperature, it influences salinity. Is it better or worse? So you can have ocean observations from the moorings and see how, or from Argo, and you can see the fit to the observations. And you can see that when there is not scatterometer data, the fit to the observations decreases. This is quite a couple data simulation, couple Earth system modeling and simulation in general is very challenging and it's very ambitious. So we really need community engagement. And I think this is one slide that it shows some ideas on how the community could work for the production of Earth system reanalysis, but probably it applies to other elements of production or forecasting systems. And it shows that okay, the production may need to be done only in one place, and it's better to do it once we have the capabilities in an integrated manner with all these components, because we will make better use of the observations and we will have the best solution. However, this is going to be probably that could be a global activity, that it will not have the resolution that is needed by many regional aspects. You will have to downscale for sectorial applications. You may want even to refine the uncertainty. So all of this can be done in different other institutions. But also the community can help on all the software modeling processes, data simulation, new observations. This is research and development. So community engagement also on the research and development. And of course, we need the computer capabilities and the databases. So I come to my summary now. If I can summarize what I said, is that one observation contributes to many aspects of the forecasting system: initialization, model development, calibration, and verification. Objective evaluation is difficult, and scientific expertise and judgment should be a guiding principle for the observing system. The panorama for ocean observations is wide and getting wider, from diurnal to decadal or beyond. In particular important for ECMWF is the initializing the coupled ocean atmosphere boundary layer. So observations of these processes would be much welcome. I also wanted to say that we need continuous time series for verification and reanalysis. I hope I have conveyed that. I didn't mention much about moorings, but the moorings are the only observing system that are currently providing collocated ocean and atmosphere information of the boundary layer. So they are very useful. And the model and data simulation quality remains serious obstacle. So we need to do something to improve these systems. Just to say, we are in a new era for ocean observations, especially with the coupled numerical weather predictions, coupled data simulation, and the S2S program. Final comments, those are just opinions, and you can take them as you wish, is that the in situ observing system is essential for weather and climate, and it needs to be sustained and enhanced. It's also essential to support satellites, especially in the ocean. Without in situ observations, we will not make any use of the altimeter data. So we want to support developments on ocean atmospheric coupling and also for reanalysis. Data rescue activities are needed in support of century-long reanalysis. Just to say that the ocean observations are currently infrautilized. And it's because the ocean data simulation systems need improving. They are not up to scratch, and they are not as good as the atmospheric data simulation. And this is better done in cooperation, but we need to do it. Finally, we are embarking on quite a lot of observing system experiments that are costly to produce in terms of computer time and difficult to analyze and require a lot of expert time. And we don't have enough adequate infrastructure to share the data and to engage the community. So I see this as a gap, and I hope we can bridge it in the future. And that's all. Thank you for your attention.
Great. Thank you very much, Magdalena, for a really interesting walk through the use of ocean observations and the coupled Earth system applications for the models. I mean, I certainly learned a lot, and we have a few questions coming through from the audience. So perhaps I can move on and ask you some of these questions. And I'll start with the first ones first. This comes from Ali, and who is asking earlier on, are you using ocean heat content for any of your analysis?
Okay, ocean heat content is a product of our reanalysis, and we use ocean temperature and altimeter to derive ocean heat content. And ocean heat content, I mean, this reanalysis from ECMWF, or S3, or S4, or S5, they have been used by the community to derive ocean heat content and studies on energy cycle on their system. So it is a product of the reanalysis.
Right, okay. So you're using that more in a climate sense for that?
Yeah, the ocean heat content is not an observation, but obviously when we simulate temperature observations, we have an ocean model, we are modifying the ocean heat content. The ocean heat content is essential for in the upper ocean for ENSO prediction. In the mixed layer is essential for tropical cyclone predictions. So yes, heat is energy, and it's
absolutely.
So we need, but it's not an observation. The observations help us to constrain the ocean heat content of our initial conditions.
And you mentioned earlier that the moorings are very useful because they co-locate atmosphere and ocean observations for you. So there's something there that's kind of quite interesting to understand. But if the heat of the ocean is so valuable for these tropical cyclones and things like that, are there preferred platforms that deliver better data than others for this? Do you use some platforms more than others for this site?
Yeah, obviously a tropical cyclone can happen in the tropics almost in many places. So having something like Argo is very useful, especially these floats that they don't go so deep, but they sample the upper ocean more frequently.
Yep.
So you can have updates of these Argo flows, that they are shallower Argo flows. I don't know whether you have a name for them.
Rapid cycling Argos, I think. But...
Rapid cycling Argo. So those are very useful for weather and extended range forecasts. Yes.
Okay, that's interesting. Right, I'm going to grab another question. This is also from Ali. What is the impact of scatterometer-derived pressure fields on cyclone prediction? So we're back with the cyclones.
Okay, that's not my topic of expertise. Okay. I know that they are continuously doing experiments because we assimilate the scatterometer and it's considered to be essential to improve the prediction of tropical cyclones. So I imagine that the scatterometer winds improve the tropical cyclones. Otherwise, we will not be using them.
Okay. Yeah. Then we have another one from Michael McFadden, and he is asking about TPOS 2020. Have you come across TPOS 2020 as let's say an ocean observing system and project? And he's asking that TPOS 2020 proposes to significantly reduce the number of TAU moorings in the off-equatorial regions of the tropical Pacific in the next few years. Do you think this is a wise strategy given the advent of coupled data assimilation, coupled reanalysis, and S2S forecasting?
It's funny, thank you, Mike. Yes, I know about TPOS 2020. They have to make very difficult decisions there. So I don't know whether they are wise or unwise. It's difficult to judge. Obviously, as a scientist, we always want all the information that we can. And I have to say, but this is just very recently, I was looking at some errors that we have in our forecasts just north of the equator. I noticed that the line at 8 north has been removed and that we don't have salinity either of the equator. I don't know whether it's wise. I miss it, but everything, but it's me. I cannot talk about the whole community for that.
Perhaps another question is are you involved in analysing the impact of TPOS 2020 at all? Is that part of kind of a feedback loop that you will be involved in to work out what, because as you say, I think they have to make some kind of strategies and payoffs for the observations there.
Yeah, I was involved at the beginning, but then there are many things to do, and I thought I was not going to have the time. So I follow it from, I keep in touch, but very lightly. So unless I'm prompted, I don't react.
Okay. So we have another question from Gregory Smith. Could you comment on the adequacy and role of polar observations for coupled predictions?
Hello, Greg. Could I comment? Well, I know that with the year of polar predictions, there are going to be quite a lot of observational campaigns for in situ observations that it will be very, very good. I don't know whether they can be sustained. We know that we have the poles are very unknown, almost as unknown as the deep ocean in the sense, and we need ice thickness, we need snow depth, we need surface temperature, we need many things. Hopefully with the, as I said, with the year of polar predictions, there will be some steps on that direction. We are trying to be engaged as much as possible because the sea ice is also gaining a lot of relevance in our predictions.
Yeah. And that's ongoing at the moment, isn't it? The year of polar prediction. Yeah.
Yes, it's ongoing. It's ongoing at the moment. Yes.
Okay. I have a couple of comments from Fabrice Bonjean or Bonjean. First of all, saying thank you for the great talk, which is really nice to hear. And asking about ENSO, let me read this correct. For ENSO 3.4, Nino index is best predicted with 0.9 correlation at 4.5 lead time. So yes. I guess that's the comment, yeah?
Yeah.
And the question is, what is the state-of-the-art status for mid-latitude predictions? How many weeks or days for such performance, and how much increase is expected from ocean observation use?
Okay, then I had that slide, but let me see if I can show it. It is here. Let me hide the slide. It's not so easy to measure, and depends. There are many variables. No, we have many variables. You could have temperature. You have a precipitation. In this case, that's the skill score on temperature, and this is on precipitation. You can see that the significance is. I mean, here we are struggling with the statistical significance, especially when you go to the atmosphere. But you predict, it's possible to predict SST and 2-meter temperatures at the different lead times. Obviously, ENSO is the one with highest skill. But the others, the Indian Ocean, the Atlantic, we have a useful skill in many areas of the globe. How this skill translates into a skill in mid-latitudes weather, that's very, very difficult to assess. So we have to be based not on statistics, but on principles. I mean, we try to combine the two, both the statistics and scientific principles, and try to build the systems little by little, guided by what we think is right, the right approach. Otherwise, if we were to look just at whether the precipitation over Europe improves, it's a very high fruit to achieve, so we will never attempt it. So we have to go little by little. I put Nino 3.4 because we need to have some benchmark to measure progress in general. But when we implement a new system, we look at other variables, obviously.
Okay, that's very interesting. So I'm going to pass to, you're getting a lot of questions here. I'm sorry, we're going to keep you working right to the end of the session. But that's really good news. And it's a fabulous opportunity to be able to, you know, to ask an expert around, you know, around this really, really interesting and important topic. So we have another one from Andres D'Agostini, saying, what currently are the main demands regarding the physical equations? So moving to a slightly different topic, not computational numerical methods or data assimilation issues, for example. What's the physics that yet needs to be described and included in the most basic equations? So perhaps a question more about, you know, and the follow-on one is, you know, do you need observations for the processes that are missing as well?
Yes.
Anyway,
yes, observation for the processes, and one of them is the ocean mixing, the vertical mixing, for instance. I mean, there may be thousands of examples, but I can think on one very immediate, is the ocean mixing in the it's very important for SST, for the atmosphere, for the heat content, for the energy cycle. And for that, you really need to have the correct parametrizations, because I don't think we can resolve it numerically. So having the correct processes, how to define this. I don't know. I know two schemes, two models. There probably are others, but none of them are good enough. So we need to improve mixing length of turbulent energy. Yeah.
Well, I mean that's quite surprising to a physical oceanographer like myself, because we're thinking, you know, that's one of the basics of ocean study. So it's just quite surprising to me that is one of the things that the model still needs to get right. But I guess it's the amount of different processes that could be involved that makes it complex.
Yeah, it's very different, the mixing in the mid-latitudes and in the tropics, the mixing of momentum and the mixing of energy and the mixing of temperature. So it's not solved, that problem at all.
Right.
The other is parametrization of boundary currents. I mean, the other thing is how can we parameterize? We cannot afford having very, very, very high resolution, and yet all the boundary currents, you see these errors here. So
yes, boundary currents are vital.
Yeah.
And certainly a kind of a personal interest of mine. Right, so let's have another question. And this is from Drew Peterson, saying you showed the impact of the MJO, the Magdal-Julian oscillation, and therefore tropical observations on extratropical circulation. What is your take on the role of extratropical ocean observations on extratropical circulation?
Okay, as well, obviously, I think I hide that slide as well, but you can see here in this slide, you have the biases of the model, seasonal forecast, and here the scale. And you see this negative scale here that has to do with the subpolar gyre. And this is because the model doesn't capture well the decadal variability associated with the decadal variability of the subpolar gyre. This is a question of observations, it's a question of models, and it's a question of data simulation. But we are finding very useful to have the rapid data and the Florida Strait cable to try to identify what are the reasons for this decrease in scale, this hole in scale. So independent observations for verification is very useful. I guess one example, there may be many others, if it helps.
Okay, that's interesting. I mean, it sounds almost like in some of these areas where you're not sure of the skills, if you could get some extra observations at some point in time that you could help track down why, you know, what the issue was, that maybe there's some kind of interactive component between observations that may not be required all the time, but required to help improve the skill of the model, which could be useful. Is that a correct interpretation? Or?
It is correct interpretation, and probably there are observations, and that's what I meant before about community engagement. We cannot tackle all these problems, and I would love to collaborate and to say, can anybody help us to understand what's happening here,
Okay.
at the ocean, etc., etc. But we don't have the database infrastructure yet, and so.
In some sense, yeah, I think you're right. And anyway, so I might touch back on that point a little later on towards the end. I'm going to take another question now. And this is from Anish Subramanian. Sorry if I pronounced your name incorrectly. Again, saying a really great talk, and thank you very much. And could you comment on the role of adapted ocean observation platforms such as gliders or remote sail drones? And perhaps in a way, this is linked to the last question, to observe and improve extreme weather predictions in regions with less ocean observations. What new ocean observation platforms are exciting for you in terms of improving predictions?
Yeah, gliders. I have to say that I'm not very familiar with gliders. I know that we analyze them, and they could be very good, for instance, for going across fronts and getting close to the currents. I mean, targeted observations is something that it has been tried with the atmosphere. It's quite expensive, and I'm not so sure whether we are ready. If I'm completely honest, I'm not so sure whether we are ready to make the most of them. But I think if you have a research study, a topic, go for it. But I wouldn't say that weather prediction is going to make with the systems that we have now. It's not where you are going to see the observations shine. So it's better for specific campaigns for the time being, I would say. But right. An opinion, I don't know.
It's interesting because you mentioned boundary currents earlier, and I know that sort of the ocean, the glider community is forming sort of an ocean glider network similar to the Buoy network and Argo and things like that around the glider platform, and one of their monitoring lines is boundary current monitoring, and so there is quite a lot of boundary current monitoring going on in the world.
Yeah.
different boundary currents. I mean, there's moorings and other systems already in place, but quite a lot of new activity with gliders, and that and these might, you know, they're just eastern or western boundary currents, even in the Mediterranean where I was last working. So
Okay.
that may be a sort of a sweet spot for both gliders and a need for weather forecasting.
Yeah, that's yes, you are right, and maybe I misunderstood the meaning of targeted in the question. And NWP, targeted observations, is when you go at a given time and deploy some data for some specific event. However, if there are boundary currents are always there. So if this is sustained effort of monitoring boundary currents with gliders, I think it would be very useful. In general, if it's a specific campaign, it will be very useful also for research, because we will learn a lot and probably help with the models. But if it's just because there is a tropical cyclone and you want to send the glider to the ocean to see, it could be very good to see what it does. I'm not so sure whether our data simulation will be able to use the observation properly. So I would leave it as the last of the reasons to send the glider under a tropical cyclone.
Yeah. So it sounds like the
study for science, it will be very useful.
Yeah, so it sounds like some sort of greater connection between the glider community could be useful there.
Yeah.
Yeah, and I guess yes, when you mentioned also the expense of doing targeted observations, you're absolutely right. I mean, you know, if we all had oodles of money, we could observe perhaps perfectly, but you know, there is some kind of payoff versus the improvement, and I guess that targeted observations as such in front of events may need to come down in price in some way, and you need to be able to express the value that you'll gain from making that investment, I guess, for that to become part of the regular monitoring in one way or another. Thinking out loud, yeah. Okay, so, and I just wanted to make a quick note towards the end. You picked up and said that it was working with the research community was something that would, you know, to help sort of improve the whole system, and certainly from the GOOS perspective, you know, within ocean observations, that quite a lot of work is still undertaken, and a lot of observations are undertaken within the research community, not yet operational, though there is some movement towards that, and certainly for some of the real-time, more weather forecasting ocean observations from drifting buoys and some of the surface moored buoys. These are already operational, and an Argo, although coming out from the research community, is pretty much an operational system as well. But let's say from the collective of the GOOS ocean sort of observation side of things, there is a real need and desire to connect into people like yourself who are using observations in order to help create that two-way dialogue over where and how the system could be improved to improve your forecast. And so it's been really interesting for me, and I have to thank you very much. I take away many good ideas from your talk and a deeper understanding, and I'm sure that from the comments that we received with the questions and the flow of questions, that many other people also enjoyed the talk. So I'm going to sort of wrap up now and say thank you very much, Magdalena. It's been a real pleasure to have you presenting, and it's been a really super interesting and useful talk. And just to let everybody know that the webinar, it was recorded, so that will then become available online on the GOOS webinar site, and I don't know if the attendees maybe get a reminder or something, but that means that if you wanted to share it with any of your colleagues who didn't have the chance to catch this, then you can obviously share the webinar link. And with that, I'll close and say thank you very much to all the audience for all the good questions and for attending another In the Goose webinar series. And again, to Magdalena for a really great talk. So thank you very much.
Thank you very much. My pleasure. Bye-bye.
Bye.
Bye.